Today I'll be looking at question 5 of the June 2011 F324 paper. Part A of the question is a gas chromatography question, and it says, explain how GCMS enables the compounds to be identified. To answer this, I wrote that gas chromatography is used to separate the components in the compound, and to identify what the different components are, you compare them to previous data. Part B of question 5 says that compound F contains carbon, hydrogen, and oxygen only, and contains 54.2% oxygen by mass. The molar mass of compound F is 118 gas per mole. Show all your working. To answer this question, I times 118 times 54.2 to get 6395.6 and divide this by 100 to give you 63.956 and round it up to 64, and that proves the number of oxygens. So there's 4 oxygens. To work out how many carbons and how many hydrogens there are, you take away 64 from 118 to give you 54, and you know that carbon, the relative atomic mass of carbon is 12, so you times 12 by 4, and that gives you 48, and that proves the number of carbon atoms, so C4. And to find out how many hydrogens there are, you take away 48 from 54 to give you 6, so that gives you H6, and that's how you work out the compound, the molecular formula of compound F, C4H6O4. Part BII of question 5 is an infrared spectrum question, so you have to analyze the spectrum to find out what compound F is. From here, you know that this is a sharp peak and it's between 1640 to 1750, and that proves the carbonyl. It shows the carbonyl group in the compound. And then from here, you can see that there's a very broad peak between 2500 to about 3300, and that shows the OH in the carboxylic acid group. And so you know that compound F is a carboxylic acid. Part C says compound F was dissolved in deuterated dimethyl sulfoxide, and some TMS was added to produce a proton and a mass spectrum. The peak at 3.4 would normally be expected at a chemical shift about 1 ppm to the right, i.e. at 2.4. So use the chemical shifts and splitting patterns to deduce the structural formula of compound F. From the spectrum, you know that this is a peak at 0.8 ppm, and also because it's between 0.6 and 1.6, it indicates the presence of a CH3 group. But also because the peak produced is a doublet, you know that for you to get a doublet, there has to be a carbon with only one adjacent hydrogen on the next carbon, and that's how you get that. So you get a CH3 next to a CH. The next peak here at 3.4 would normally be expected about 2.4, about there, and because you know it's between 2 and 2.9, using the chemical shift values, you know that this will produce it indicates that there's a CH next to a carbon double bonded to an oxygen. The next peak is at 11 ppm, and using the chemical shift values, you know that this shows the presence of a carboxyl group, so that's what you get for that. To answer this question, you just have to explain, well, I answered that the peak at 0.8 shows that there is a doublet. So there's one adjacent hydrogen on the next carbon, and so it shows that a CH3 is next to a CH, like I said before. The next peak is a multiplet, which normally is found at 2.4 ppm, and this shows the presence of a CH, C double bonded to an O. And lastly, the peak at 11 ppm shows the presence of a carboxyl group. And the possible structure for compound F is this is what I got for it. And because you know that there's 4 oxygens, actually, firstly, so to check back to see if we've got the right structure, you know that here you've got a CH3 which is next to a CH, and there's 1 carbon there, so this is the double. It's C4H6O4. You know that to me from this part of the structure alone, you've got 3 carbons, 5 hydrogens and 2 oxygens, and you're from using the molecular formula, you know that you're missing 2 more oxygens, 1 carbon and 1 hydrogen, and the molecule that makes up for this is another carboxyl group, so you get another carboxyl group at the next side of the molecule. So this is what it looks like all together. The second part of question 5C says, explain why deuterated dimethyl sulfoxide is used as a solvent rather than CH3 brackets 2SO. This is because deuterated dimethyl sulfoxide doesn't produce any peaks because there's no hydrogens present in that compound. State why TMS was added. It was added to calibrate the chemical shape scale, or to use as a reference. A second proton NMR of compound F was obtained after adding a few drops of D2O. What difference would you expect to see between the proton NMR spectra of compound F obtained with and without D2O? And the answer to this is that the peak at 11 ppm will not be produced.